So it's rather unusual for the first video, the introductory video on a YouTube channel, to actually be a practical video. But the purpose of this YouTube channel is actually to change some existing open source software for pandemic simulation. But I thought it was important to introduce the software, and one of these aspects of introduction is associated with mathematical complexity. So the software that I'm going to base this project on is called the ApeSDK. And the ApeSDK is incredibly mature software. It's been developed since 1996. It's been used by Apple and Intel and a variety of universities. And it's had a few different names, but ApeSDK is its most recent, named iteration. And the thing I wanted to talk about here was adding thunder and lightning, basically adding atmospheric effects. So you can run the existing simulation. I'll give some indication of this. Now, there are many different sub-projects within the Ape SDK. There's a planetary simulation, there's an urban simulation, there's a kind of pitched battle simulation, all to show the, the various kinds of simulation that you could do basically with the Ape SDK. But the primary simulation is still simulating apes wandering around, simulated apes in their environment. And here's the narrative that goes on between the apes, what's going on with each ape, specifically in a kind of text format with additional information. Anyway, so there's a weather system that exists in the simulation, and also in the planetary simulation it's the same weather system. But the problem with the weather system is that it doesn't have thunder and lightning. It doesn't have, storm effects that have thunderstorms, basically. So I wanted to add this, but I wanted to show my thinking around how to add it. And I've done a bit of debugging around this. You'll see some existing code, but I wanted to talk about the underlying mathematics. So as you see here, you can turn on and off the weather, just to give a sharp indication of what the weather actually is here. It's this kind of white map that goes over the landscape and indicates the weather. And here, this is the active ape. Let's pause the simulation and move the active ape under. Okay, so let's move the active ape. And so this is obviously rain. It's a rain cloud. Ooh, did it crash? Did it crash? No, it didn't crash. Just moved off that for some reason. Anyway, so maybe not really sure what's going on here. Anyway, let's unpause it. So anyway, this is the weather that's being applied here. So let's quit out of this. Let's have a look at the weather. So you'd start with the landscape or the land generation, and you'd look at the underlying stuff. Maybe you'd search for weather. Let's try that. Okay, so a lot of the weather initially, or at least the output of the weather, comes through the land interface. And this is, how to provide an iconic representation of the weather, for example. But more importantly, you get into weather init, weather cycle. The init cycle naming is used throughout the simulation. So underlying each of the land elements, including the weather, is this notion of tiles. And this is important in the planetary simulation because the planetary simulation is based on 6 simulation tiles, obviously with 8 points within that, but 6 simulation tiles to provide a pretty good planetary simulation. So all of this is decomposed, for want of a better term, into the individual tile elements. So if we look at this, this creates the weather tiles, and it's important actually perhaps to look at the distinction between what is in the land and what is in the... So the land has a bunch of shorthand in it associated with wind values, strengths basically, dissipation, these kind of things, as well as the topography information and date information. And all the land is fractal mapped based on underlying genetics. So if we look at the tiles, let's look at one of these things, we see that it too is based on underlying genetics. It has a topology, an atmosphere associated with it, pressure vectors associated with it, and then ranges, basically, which we'll probably talk more about with regards to the actual underlying simulation element. So the init is pretty straightforward. It just creates the initial values and starts the distinction between the topology and the pressure map. Now the pressure map here, I think I can actually, if we go to the tile information, so you have a topology, you have atmospheres, and you have a pressure delta. Now, the atmosphere and the pressure is basically the movement of atmosphere information, and the atmosphere is that underlying kind of pressure information. It's the notion of, I guess, a vector and a scalar value of pressure. So the calculation of this, if we can find it, should be with a cycle. Tile, where are we? I think tile cycle, okay. So here we have max and minimum atmospheres. And here we do a calculation of where these things are. And then we get the ranges of this. So we can run the simulation and get basically what's happening with these atmospheres. What am I doing here? I don't want to do that. Cancel. Okay. So, right. So what we're doing here is there's an atmosphere shift calculation, which is just basically 2 dimensions calculated, giving a implicit direction as well. And what you want to see is when these deltas are at maximum and minimum. Minimum here is basically like 0 minus maximum. So they're top and bottom ranges, basically, where 0 is flat, no change in atmosphere and surrounding adjacent cells. So what you're calculating here is basically shift of atmospheres in 2 dimensions. So this local atmosphere value here is what's important through that. And I wanted to get a general sense of the ranges here, what's going on mathematically through this. So we're running the simulation, and we're also finding minimum and maximum atmospheric ranges and the locations where they're occurring. Now, unfortunately, this map is centered on the ape. So it might be nice to put additional graphics in showing the point of max and min. But you'll see that there's very limited transition between these points. Namely that, well, there was a max-min shift there, but namely that these are established maxima in the simulation. Now, what I was thinking of doing is working out, so you think this is increasing, but actually it'll decrease eventually. It'll hit maybe 13,000, and then it'll be adjusted, hopefully. So I predicted, maybe a little higher. Anyway, it'll get adjusted eventually. Famous last words. This is why I always enjoy recording videos, because you'll never... Yes, it'll eventually get adjusted. Well, let's wait and see. So what you see here is really the extreme ranges, and they're not actually that close. They're pretty well equidistant in the map. The map is a 512 by 512 grid to give some indication of what these coordinate points are. So as you can see, it actually increased and decreased. So it was up to here, 20, what have you, and the minimum didn't actually decrease, the maximum decreased. So you see, yeah, now it's decreasing in the minimum as well. So you see that actually it's not ever increasing, that there are various adjustment points. But what we would be looking for here is a way to establish thunderstorms and what characteristics would give thunderstorms. Now, it would be at these high gradients of pressure because there's basically electrostatic force in those high gradients of pressure as well. And what you need to think about is what mathematically does a thunderstorm mean at that location? Well, it means some recalibration of the pressure. But in a sharp delta, it's also very difficult to recalibrate that pressure. So you basically need to create almost like localized flattenings. So maybe 2 or 3 by 2 or 3, maybe almost like a circular interaction, where you were doing normalization over that area. And that would be the thunderstorm area. You'd work out where the center of the thunderstorm would be through this, and then you do normalization through that. And obviously, you'd add light effects here as well to show that. So this, I'm going to write code to this effect and then record a video following explaining what the code actually does. But yeah, it's very much, and rather than just picking these max and min points, it would go through and find however many of the thunderstorms that were needed. Maybe it might be interesting actually to establish a kind of maximum range thunderstorm. I would think probably, I don't know, maybe 64 thunderstorms at most in a simulated map. But what you would have is a lot of these areas like this, where you have really strong distinctions between, high pressure, low pressure. You'd have a thunderstorm which would resolve that in some way. So that would add a texture, for want of a better term, to the weather simulation as well. So what I'm going to do is write that code, record another video, come back and show that video, and I'll probably also show more introductory videos as well, just going through different parts of the code, very similar to what I've done here, associated with the weather specifically, but look at other aspects of the code, moving towards, like I said, using this open source software to produce a pandemic simulation, which will be coming through the videos on this channel. Please do get in contact with me if you're interested in more feedback. Leave comments, these kind of things. I'm very much thinking about this as being an interactive, just through comments, an interactive way of explaining how these things are done. But anyway, so this is the Last Monkey Standing YouTube channel. Look forward to any initial feedback and comments, and I'm more than happy to make videos that explore different things. So for example, if you want a video about how to download the source code from GitLab, get it running and all this kind of stuff, I mean, I can do those kind of videos too, just to explain to people how they can get the software up and running on Mac or Windows. Linux, I think we could probably get a Linux port. There has historically been a Linux port, but the two versions that I maintain are the Mac version and the Windows version of Simulated Ape. And yes, I can also talk about the other simulations, the urban simulation, these kind of things, if you're interested as well. The planetary simulation is pretty cool as well. So I think what I'll do is once I add thunderstorms, I'll go to the planetary simulation and run that to show the thunderstorms in the planetary simulation too. Anyway, I hope you've enjoyed this video. Please do leave comments, like and subscribe as well. I always forget to say that in various YouTube videos that I create. So like and subscribe, and let's continue the discussion through the comments in this video.